Okay, in this video we're going to look at timber column design, and we're just going to jump right into it by looking at example 18.9 from the textbook. In this example we are asked to design a square column, and the reason I want to point this out is because I have seen more times than you would imagine examples where I have on a test asked students to design a square column, and they end up specifying columns like an 8 by 10 or 4 by 6, and those would be rectangles, but they are not squares. So this is specifically telling us we want a square column whose base and height are equal to each other. So when it says square, it really does mean square. So we want to design a square column. That's going to actually help us out because it reduces the number of options. We basically have a 4 by 4, 6 by 6, 8 by 8, 10 by 10, etc. So we're looking at supporting a compressive load. So P is equal to 45,000 pounds. And the unbraced length of the column is 14 feet. Now, if you follow the textbook example strictly as the textbook does it, they just simply take the load divided by the allowable stress, which they just simply assume is equal to the compressive stress parallel to the grain, the value that comes from the appendix. To me, that doesn't make a whole lot of sense, though, because if you look back to our previous problem in which we did an analysis, we found that the allowable stress, which is equal to the compressive stress parallel to the grain multiplied by C sub P. And in our previous example problem, we found that C sub P was, I think it was about 0.86. Okay, so the allowable stress in a column is not going to be equal to this full value, this F sub C from the appendix, but some percentage of it based on the slenderness of the column. And unless we have a very short, very stout column, this C sub P value is not going to be equal to 1. It's going to be equal to something less than 1. And in fact, if we look at our column, it's 14 feet tall. For a timber column, I would say that's getting to be pretty tall. So I think it's unlikely that our C sub P value is going to be equal to 1. I would personally reduce that. Use something similar to what we found in our previous analysis problem, like 0.86. So I'm going to vary from what is in the textbook slightly, only because I think it will lead us to our final design more efficiently. So I'm going to take the load, which is 45. Here, I'll write it down over here. Load is going to be divided by F sub A. And so our load is 45,000 pounds. And rather than simply dividing that by F sub C, which I guess I should also mention that this is a Douglas fir. And so Douglas fir is the same wood species we used in our analysis problem. It has an F sub C value of 1,050 psi. So the textbook just takes the 45,000 pounds divided by 1,050 psi. I think we need to reduce this because I'll go ahead and spoil the ending here. If you follow the textbook solution, they choose an 8 by 8 and find that it's inadequate, and so they have to bump it up to a 10 by 10. And that's a lot of work. You're basically having to do the problem twice. So I'm going to guess that our previous analysis problem was 0.86. Maybe I'll guess that this is around 0.85, the stability adjustment factor. So in that case, our load divided by stress, which is going to give us our area that we're going to want to start off with, is going to be about 45,000 divided by 1050 times 0.85. And I'm getting from this about 50. So about 50 square inches. So I guess I didn't write over here, but area is equal to load divided by stress. And that's what we're finding here, area. And this is just a guess. Just like with steel columns, our design approach with timber columns is essentially a guess and check process. So we are guessing that we need an area of about 50 square inches. So if I turn to the appendix and look for a square timber column that has an area of 50 square inches, let's see which size column that's going to lead us to choose. So I'm looking in the appendix and I see that an 8 by 8 has an area of 56.3. So it turns out that even, and again I have the benefit of foresight here, I know how this problem works out, but even using a stability adjustment factor of 0.85 still leads me to guess 50, which leads me initially to assume that an 8 by 8 timber will be adequate. I happen to know, looking ahead, that it will not be, but if this were an actual design problem with an unknown solution, we would have no way of knowing that as of right now. So based on the information provided to us, it would make sense to start with an 8 by 8. I think the reason why it's going to end up turning out that an 8 by 8 isn't adequate is because of this unbraced length being relatively large, 14 foot timber column. That's kind of long. So at any rate, if we do go with an 8 by 8, its area is, well, I've got that written down here already. The area is 56.3. What else do we need to know? The D, the least dimension size, is 7.5. Let's see, any other pieces of information we need to know here about an 8 by 8 column? No, the I and S is used for beam design. Okay, so that ought to do it. So let's start analyzing our 8 by 8 column that we've chosen. We should verify before we proceed that LE over D is less than 50. So our unbraced length was 14 feet. 14 feet is 168 inches. And it is a pinned pin, so that's just 1 times 168. So we don't need to adjust the length based on the support conditions. And the D, the least dimension, is a 7.5. And so 168 divided by 7.5 is equal to 22.4. And so that is less than 50, so we may proceed. This column is not too slender. The next thing we need to do, I like to start with alpha, and then go to CCP, and then find the allowable stress. So alpha is equal to 0.3 times E. E is the modulus of elasticity, and for Douglas fir, which is the same species we used in the previous example, that's 1.7 million psi. So 0.3 times modulus of elasticity divided by LE over D. The slenderness is 22.4. We're going to square that and then multiply it by F sub C, which is 1050 psi. Again, that comes from the appendix for a Douglas fir. And that should work out to be 0.968. Once we know alpha, we can plug that into our C sub p formula. C sub p is going to be equal to 1 plus alpha, so it's going to be 1.968 divided by 1.6 minus the square root of, again, 1 plus alpha is 1.968 divided by 1.6, square that, and then minus not 1 plus alpha, but just alpha in this third term, 0.968 divided by 0.8. So again, if you need to, break it down into these 3 separate terms, find them individually, then solve. In the interest of time, I'm just going to jump straight to the final answer here for C sub p. Once we plug that all into the calculator, we should get 0.680. That's our stability adjustment factor. And this is a bit of a tip-off right here, 0.68. That is less than the stability adjustment factor I took a guess at initially. And so that is why it's going to turn out here in the end that an 8 by 8 is not adequate. If we then take our, to find the allowable stress, if we take F sub C times C sub P, it's going to be 1050 psi multiplied by the stability adjustment factor, which is pretty low, I think because of the relatively large height of our column, and that turns out to be only 714 psi. If we then take our 714 psi and multiply it by the area of our column, that will give us the allowable load. So our allowable load equals the allowable stress multiplied by the area. The allowable stress was only 714 psi. We multiply that by the area of an 8 by 8 column, which is, let's see, I think I wrote that down earlier. Yep, up here, 56.3 was our area. So we got 56.3 square inches. And so if we multiply, let's multiply that out, 714 times 56.3. That gives me 40,198 pounds. But the problem statement told us that we had to resist a load of 45,000 pounds. And that is, sad face, no good, NG, no good. So the 8 by 8 is not going to get the job done. So that means that we need to choose a larger column. Since the problem statement restricts us to square columns, the next largest size would be a 10 by 10. And I don't, well, let me try real quick. No, I don't think I'm going to. I'm already past 14 minutes. I won't be able to get through the entire analysis here to show you all the equations. But if we jump to the result, the allowable load for a 10 by 10, if I go through all the steps, comes out to be 77,600, which is greater than 45,000. Quite a bit so, in fact. In fact, if that was our original choice, we may be tempted to try the smaller size because that seems too big. But we've already proven that an 8 by 8 doesn't work, so the 10 by 10 is the best option here.